In chapter 3, we will look into different kind of measurements that we have to analyze a data set. We start off with measures of central tendency, where they describe the center point of our data set with a single value by using the mean, the median, or the mode. So the measures of central tendency are basically your 3 M's. You have the mean, the median, and the mode. The mean is the mostly common measurement used of central tendency. It is calculated by adding all the values in our data set and then dividing the results by the number of observations. We use the letter mu for the population mean. Keep in mind again that population parameters are presented with Greek letters, and the sample mean we use X bar. One drawback of the mean is the fact that because we take into account every single entry in our data set, if we have outliers, then, and again, what do we mean by outlier? Outlier is an entry that's significantly higher or significantly lower than a typical entry in a data set that can heavily influence the outcome of the average. So the formula for the mean, new population mean, is the sum of all the entries in our population over the population size. Sample mean, the sum of all the entries in our sample over our sample size. Now, the median is the value in the data set for which half of the observations are higher and half of the observations are lower, which means the median is the value in the middle of an order data set. If we have an odd number of observations, the median will be the value of the middle ranked observation. If there is an even number of observations, then the median will be the average of the two middle values. The median is more difficult than the mean to calculate manually, but it is not influenced by outliers because it's in the middle of the data set. On the other hand, the mode is simply the entry that appears the most often in the data set. The mode is particularly useful when it comes to describing categorical data. The mode might not be unique in a data set or even exist in a certain data set. That means you might not have a mode in a specific data set, or you may have 2 or 3 modes, as long as we remember that the mode is the entry with the highest frequency. The shape of the distribution now. In determining the shape of the distribution, we compare the mean, the median, and the mode. If the mean, the median, and the mode are roughly equal, then we have a symmetric distribution or bell-shaped distribution. If the median is higher, greater than the mean, then the distribution will be skewed to the left. That means you will see a longer tail forming to the left. And if the median is less than the mean, then the shape of the distribution will be skewed to the right. That means longer tail to the right. Let's look at this example. So you are given a data set, and you are asked to calculate the mean, the median, and the mode, and also determine the shape of the distribution. To find the mean, we add them all. We have n is equal to 9. We divide by 9. The average will be 2.678. The median, you first place your data in order. We have an odd number of entries. Therefore, the median will simply be the value in the middle, which in this case is 2.6. Now, when you place your data in order, you can see straight away that 2.6 is the only entry that occurs more than once, which automatically makes it into the mode as well. The shape of the distribution, since the mean is greater than the median, the shape of the distribution will be skewed to the right. And again, keep in mind that we only have 9 observations. Now, when it comes to measures of variability, the measures of variability determine how much spread is in our data set by using the range, the variance, and the standard deviation. We had to use the range before when we were calculating the class width. the range is maximum minus minimum. As you can see, the range is easy to calculate and understand. However, it is also easily affected greatly by outliers, because we only use maximum and minimum. If one of these two is an outlier, then you can imagine what impact that will have on your range. Now, the variance measures the square difference between each data point and the mean. The letter for the population variance is sigma squared, and for the sample variance is S squared. So whenever you have the squared, you know that this is your variance. To calculate the variance, we first calculate the sum of all the entries, and then the sum of all the squared entries. We will be using the computation formula to calculate the population variance and the sample variance. Once again, population variance, sigma squared, sample variance, S squared. For the first formula, for the population variance, we take the sum of the square entries minus the sum of all the entries squared over the population size, and all of this over the population size. For the sample variance, again, we take the sum of the square entries minus the sum of all the entries squared divided by the sample size, but now we are dividing by n minus 1. The reason we use n minus 1 in the denominator for the sample variance is to better estimate for the true population variance when compared to dividing by n. Now, the standard deviation, as soon as you have the variance, the standard deviation is very, very easy to calculate. You simply take the square root of your variance in order to find your standard deviation. Regardless if that's a population standard deviation or a sample standard deviation, you simply take the square root of your variance. So, population standard deviation sigma is equal to the square root of the population variance, sigma squared. Sample variance is equal to the square root of your sample variance. When we talk about the coefficient of variation, the coefficient of variation measures the standard deviation in terms of its percentage to the mean rather than units to the mean. When comparing two samples, the smaller coefficient of variation indicates more consistency, less spread from the mean, basically. The formula for the sample coefficient variation is S over X bar times 100%. It's always a percentage. The coefficient of variation is always in percentage, and we calculate it by taking the standard deviation and dividing it by the average times 100%. So, for this example, the following data represents the number of papers published from 8 professors last year. This is the data set that we have. We want to calculate the range, the variance, the standard deviation, and the coefficient of variation. So, we have n equal to 8, first off. We want to find the range. We will do maximum minus minimum. 6 minus 1, this is equal to 5. Now, to find the variance, we start off by calculating the sum of all the entries. This is what this means. Keep in mind, this is the capital case, sigma in Greek alphabet. Whenever you see this symbol, it means the summation of whatever follows it. The sum of x means that you simply take all the entries that you have in your data set and you add them. If we do so, this will be 24. The sum of the square entries, you take each one, you square it, and then you add it. All right, so the sum of the square entries in this case will be 88. So when you go to your formula, the formula for the sample variance, you enter the sum of the squared entries that we found it to be 81 minus the sum of entries that we found it to be 24 squared. Don't forget to square it, 24 squared, over the sample size, and all of that over n minus 1, 8 minus 1 in this case, which is 7, and we should find 2.286. Be careful with the order of operations here. Calculate your square, divide it by 8, subtract from 88, and then divide by 7. Make sure you do not make calculation errors. The standard deviation, whatever I got here for my variance, I will take the square root of that, and that will give me 1.512 for the sample standard deviation. Coefficient of variation, all I need is the standard deviation that I just calculated, right? And then the average. So all I need to do for the average is what? I have the sum of all the entries, 24. I have the sample size is 8. 24 divided by 8 is 3. So your coefficient of variation will be 50.4%, which is high. Usually anything below 20% indicates a low variability for your data set. So 50.4% indicates high variability. Now, when it comes to the empirical rule states that if a distribution follows a bell-shaped symmetrical curve centered about the mean, so the empirical rule applies only to normal distribution, bell-shaped distribution, and it states that 68%, 95%, and 99.7% of the values will fall above and below 1, 2, 3 standard deviations around the mean, respectively, which means if you want to see between which 2 points 68% of the observations fall, then all you need to do is add and subtract 1 standard deviation from your average. If you want to know 95% of the observations between which 2 values they fall, all you need to do is add and then subtract 2 standard deviations from your average. And if you want to find almost all the observations between which 2 values they will be, all you do is add and then subtract 3 standard deviations from your average. So basically, if you have the average and the standard deviation, you can find the 2 values that you will have this specific percentage between the 2 values. Let's look at this example. In the sample mean, if the sample mean is 8 and the sample standard deviation is 1.5, then 95% of the observations will be within which 2 values? Of course, given the fact that our distribution follows, it's a bell-shaped distribution, follows normal distribution, 95% is 2 standard deviations from the mean. So x bar plus minus 2 standard deviations, 8 plus minus 2 times 1.5, which is 3, 8 minus 3, 5, the lower limit, 8 plus 3, 11, the upper limit. So 95% of the observations will be between 5 to 11. This is basically what you have just calculated. Now, when it comes to measures of relative position, the measures of relative position compare the position of a single value in relation to other values in the data set. So basically, you're looking into the standing of a specific value in comparison to the other data values that you have in your data set. The measures of relative position are the percentiles, quartiles, and the interquartile range. So this is where we want to pay a little bit attention when it comes to the percentiles. The percentiles measures the approximate percentage of values in the data set that are below the value of interest. In order to find a specific percentile, the first thing we do is we place the data in ascending order and we calculate the index I. What I want you to remember is that the index I will not give you the value of your percentile. It will give you the position of your percentile. You calculate index I by calculating P over 100 times N. P will be whatever percentile you're looking for. Let's say you're looking for the 30th percentile, P will be equal to 30. You're looking for the 70th percentile, P will be equal to 70. And N, the sample size of your data. Now, the tricky part starts after you calculate the index I, because once you calculate the index I, you're either going to end up with a decimal or with an integer or a non-integer. Now, if I is not an integer, what you need to do is round up. You round up to the next convenient number, and the specific percentile will be the value in the position that you have rounded up to. If I is an integer, then the specific percentile will be the average of the value in that position plus the next position. And this will become a bit more clear when we go through the examples. Quartiles are nothing but specific percentiles. We have 3 quartiles. We have Q1, Q2, and Q3. Q1 is P25, Q2 is P50, also known as the median, and Q3 is P75. So you calculate them the same way as the percentiles. The quartiles will separate your data set into 4 equal parts. The interquartile range is the difference between the first and the third quartile. IQR, Q3 minus Q1. So let's take a look at this example. The following data represents the age of 9 students in the Cape Cod Community College. So we know from here that N is equal to 9. We want to calculate the 20th percentile, the 65th percentile, Q1, Q3, and IQR. First thing we do when we calculate percentiles or quartiles is place the data in order. That's really, really important, and you cannot forget that. So we always place the data in ascending order. I want to calculate the 20th percentile. I will be equal to 20 over 100 times 9 because N is equal to 9. This will give me 1.8. If we have non-integers, we said that we round up to the next convenient number. 1.8 becomes 2, which means, and this is what I want you to pay attention to, that the 20th percentile is not 2, is the value in the second position, right? So what value do we have in this? What is the second position, position? That would be 19. So your 20th percentile will be 19. That means that 20% of your data falls below 19 and 80% of your data falls above 19. 65th percentile. I is equal to 65 over 100 times 9. This is equal to 5.85. It rounds up to 6. We take the value in the 6th ranked observation, which in this case is 25. Q1 is P25. 25 over 100 times 9, 2.25. We round up to 3, and we take the 3rd ranked observation, which once again is 19. So Q1 is equal to 19. Q3, P75. 75 over 100 times 9, 6.75. We round up to 7. The 7th ranked observation is 26. So Q3 is equal to 26. IQR is 26 minus Q1, which is 19. So 26 minus 19, 7. Now, when it comes to the z-score, that's another very, very important measurement in statistics. The z-score identifies the number of standard deviations a particular value falls from the mean. If it's positive, then it falls above the mean. If it's negative z-score, then it means that your value falls below the mean. The formula for the z-score, for the sample z-score, is x minus x bar over s. So x will be the value that you are calculating the z-score for. X bar is your average, s is your standard deviation. So if we want to find the z-score for 150, if the mean is 120 and the standard deviation is 25, we will do 150 minus 120 over 25, which is equal to 1.2. It's positive. So that basically indicates that 150 is 1.2 standard deviations above the mean. When you're asked to provide a 5-number summary, you want to provide minimum, Q1, Q2, Q3, and maximum entry. We use the 5-number summary to create a box and whisker plot, where it's a graphical display showing the relative position of the 3 quartiles in comparison to the mean and the maximum value in your data set. The ends of the plot represent Q1 and Q3. The line in the middle represents Q2. The whiskers represent minimum and maximum respectively. Outliers are values that are much higher or lower than most of the data. The upper and lower limits of outliers will be Q3 for the upper limit plus 1.5 interquartile range times the interquartile range. The lower limit, Q1, minus 1.5 times the interquartile range. So in this example, for the data in example 4, provide a 5-number summary and a box and whisker plot. We place the data in order. We know that the minimum is 18, the maximum is 41. We've already found Q1, Q2, Q3. Q1 is 19, Q3 is 26, Q2 is your median, the value in the middle, the 50th percentile in other terms. And if you were to look at this way as well, you could do so. You start with the minimum. This is your maximum. You have over here is Q1, where the line is. I'm not sure if you can see it through here. Might not be as visible because of the color. It's over here. Q3 and maximum entry. In addition to the notes, you should take a look also at the objectives for the chapter. You have all the main formulas for all the terms. This is a big chapter, so you want to make sure that you are familiar with all the formulas. You have all of them combined, as well as key terms that you will find in your notes. So this concludes the notes for chapter 3.